Hi everybody. This is first lecture of multicollinearity. This is related to everything else we've been doing, and particularly the last several lectures where we introduced the items dealing with the correlation between not only the predictors and the response, but between the predictors. So now we want to look at this a little more closely and see how this affects the model. Uh, Now, the book begins by considering cases where you have two predictors and they're completely uncorrelated or completely correlated. That is, the correlation coefficient is 0 or 1. We'll do a similar thing, but not in it. Maybe we'll focus more on just the more practical case where there's a low correlation versus a high correlation. This is almost always either some correlation and almost always never perfect correlation. So let's just start with two predictors, and from there it gets, it quickly gets more complicated. It's the same ideas, but it's just more to deal with mathematically, and just keeping track of everything. So we just want to get the idea across to start. Okay, so let's see. So let's say we have two, so let's call this collinearity. And this is dealing with correlation between predictors. Okay. All right. So suppose we have y beta 0 plus beta 1 x1 plus beta 2 x2 and y star beta 1 star x1 star plus beta 2 x2 star. This is the standardized. Okay, and so to get B star, so there's two things we want to see that happens. We want to see when, so two cases, so maybe more than two cases, so several cases. So let's consider x1, x2 to be uncorrelated perfectly. This will be quick, correlated because it's not realistic. And just say correlated, right? Or highly correlated. Which could even be a coefficient of not that much, but just something where they're correlated. Okay, so three cases there. All right, so recall from the previous lecture, so avoid writing too much. Recall B star. So we're gonna identify two properties, two properties of this of the linear regression that occur when based on how correlated these two predictors are. So B star, okay, it was equal to RXX inverse RYX. And then, of course, we can get B from B star, right? B was equal to SY over SK, if I want the case one, B K star. So this is related to that. So we can look at this one to start the standardized coefficient. Okay, so this was equal to, you may remember, so we have 1 over 1 minus R12 squared, 1 minus R12 minus R12, 1 RY1, RY2. And writing this out one more step, we get ry1 minus r12 ry2, 1 minus r12 squared, and ry2. Yeah, right. So this is B1 star and B2 star. And of course, from before we had, R12 is equal to the correlation, simple correlation of x1, x2. So everything still defined the same way. Our, say, yk is correlation xk with y, etc. Okay, so now let's look at the different cases and see what happens to the coefficients. So if, we mentioned this in one of the previous lectures, if R12 equals 0, then B1 star is equal to R1, Y1, B2 star is equal to RY2. You can find the estimated regression coefficients in the standardized model by just knowing the correlations of the response with each predictor. And then I can get B1 from using SY. So, and B1 equals, SY over S1, B1 star, etc. B2, okay? So, okay, so this is the same thing you would get for, now here's the point. These coefficients are exactly the same coefficients as you would get in an SLR model, an SLR estimated model with each predictor separately. Let's just write with each predictor and show it. So, for example, suppose we want y equals, let's just take the x1. Then we know b1 is equal to the sum xi minus x, let's write it like this, even though it's only one, x1 bar yi minus y bar sum 1 to n, right? Okay, so I can show that this is the same thing as this b1 here in this case, right? So, but this is equal to checking. I should probably go to something like this. Right? Okay, so that's B1, but no, so we want to show this is just equal to what? SY over S1 times, so right, so we want to show this is equal to, okay, so we'll show, also have when R12 equals 0, B1 equals SY over S1, B1 star, but BY star when R12 is 0 is RY1, which is SY over S1 RY1, which is, what's SY Sy is the square root of the sample variance of y. All right, so sum yi minus y bar squared divided by sample variance of x1 and now times ry1. ry1 is the sample correlation of x1 and y, so this should be the sum xi1 minus x1 bar sum times yi minus y bar over square root sum xi1 minus x1 bar squared square root sum yi minus y bar squared. And you see everything should cancel. Here I have the 1 over n's cancel here. The sum yi minus y bar squared cancels here. This one multiplies this one to remove the square root, so this is just equal to sum xi1 minus x1 yi minus y bar. And this term's gone, the n minus 1's gone. This multiplies this to remove the square root, so I get sum xi1 minus x1. Okay, so we get the same thing. So lesson, and this applies even if there are more than 2 predictors. So the first lesson, there's only 2, is that, so 1, when predictors are uncorrelated, their coefficients are the same, even if some are removed or added. So their estimated coefficients are the same, even if some are removed or added to the model. So let's say I have 3 now, and and they're all uncorrelated. The coefficients will remain the same. Okay. The second result concerns, well, wait a second. I want to be careful about that statement. I actually have to check that if that's true. But let's say certainly for 2, they're the same. And if we try to do it, we'll do it on a demo in a minute and see if it's true for 3. I think it might not be totally true for 3. In any case, one other thing to note is that, completely uncorrelated predictors is probably rare. And so you generally are talking about these in shades. So you have predictors that are mildly correlated, very low